These are the points related to registers. Okay. These are many details we have covered in the previous class. I just want you to go through this. Okay, these are all the things we have covered in the previous classes. We have seen serial out, serial in, serial out shift registers, serial in, parallel out, parallel in, parallel out, and this is lastly what we have discussed is universal shift register. Today we'll take up counter and let us see how this counter can be used in variety of applications. What do we mean by counter? Group of flip-flops. If you want to build a counter, you need a group of flip-flops similar to register, right? Even we give same definition for the register also. Register is a collection of flip-flops. Okay, register is just a one row in the memory. Memory contains lot of such rows. And also you should think how memory is organized. When we say 1 gigabyte memory or 1 megabyte memory, what do you understand from that? 1 megabyte means it can hold 1 megabyte information, words I can say. The byte, what I say, is a word actually. You will have totally 1 megabyte word you can store. And also memory can be categorized, probably you might have learned in computer organization. Memory is byte addressing. Every location is going to be 1 byte. Understand it? And sometimes, people memory manufacture, they don't go for higher than 1 byte. When I say 1 megabyte, there are 1 megabyte locations. They are telling the number 1 mega with reference to the locations. Not with reference to the how many bits I can store in a word, in the location. Okay, that's the thing which one should catch. Okay, counter is also very important application because it's an extension of the flip-flops. To become familiar with the counters, one need to understand how flip-flop works. And once again, you can build counters using JK flip-flop. You can build counter using T flip-flop, D flip-flop, all kind of flip-flops. Working, normal flip-flops can be used to build the counters. I don't suggest SR flip-flop to build the counter because already we know SR flip-flop has got undefined state, which we can't use it in many applications. That's the main reason why we are not using SR flip-flop in building counters. Okay, and counter is one of the important applications. In my career, I think I've built so many counters. I'm not talking with reference to teaching academic, but from research point of view, if you want to build a very complex applications, counter is very important. But the way I treat counter and today's textbook normally treat counter is a little different. Probably counter people classify under sequential circuits. In my opinion, counter is also a combination and sequential circuits. Why do I say this? I'll show you the code in the module 4 and 5. You will appreciate that. How do I classify this counter as a combination circuit? How counting normally happens? How do you count in the mind, right? You keep adding, for example, if I say count from 1, what do you do? Keep on adding 1 to that, right? Understanding? When I say add, what kind of circuits comes to your mind? And adding. Add, right? And so 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 1 is 4. Like that, so keep on adding, right? Don't you think that there's an adder in that? Understand it? So there's adder in that, right? That means I'm visualizing counter like an adder. Whenever the counting has to happen, I will use combinational circuit. Adder is a combinational circuit. Adder is not a sequential circuit. Understand it? But I use clock for that, and whenever the counter updates its state, I will store in the flip-flop. Understand it? You may ask the question, why do you do like that? Because if you do like that, the circuit becomes optimized. Because today, as I told you, we don't go to the lab and build, if I ask you to build 1024-bit counter, you can't do that. Understand? Immediately when somebody says to build, 1024-bit counter, I will go to some CAD tools. Okay, I will use CAD tool and build the counter using that. I will write a Verilog code or VHDL code or even C or C++. Nowadays you can even use those programming languages, okay, software programming languages even to build a counter. It's possible. But we normally, electronic people, we use a Verilog program. That's one of the most widely used in industry. Okay, we use Verilog code to build the counter, and that's a way you model the counter. Understand? Once everything is perfect, once functionality is, the code is verified, then you can take it to the chip level. Understand? Everything we do it in the software itself. Anyway, this is counter related to the. We are covering only theoretical aspects here. We don't demonstrate any laboratory part of this counter. But anyway, you are verifying this counter operation in the laboratory, I believe it, using some IC. Okay, commercially available ICs. You are using the IC to build the counter. There is decade counter. Okay, there is double decade counters are available in the commercial MSI form, medium scale integration form. You have to buy those ICs and test how counter works. One such IC we are going to demonstrate at the end of this topic, counter, to show how a commercial counter works. Okay, counter is basically a combination of plus sequential circuit, in my opinion. It's an example of register only. It's an extension of register, nothing else. It's not beyond the register. If you have a register, you can also build the counter. That's the idea. Primary purpose of counter is to produce specified output pattern sequence. You can produce one particular pattern sequence. You do not always increment, counter from present state to the next state. Understand? You can also jump by 2, jump by 3. That's also called as a counting, right? But generally what we see here is just an increment is called as a counter. It's not a counter. That you may call as a counter, but you can also jump by 2. Understand? We have seen that such kind of counters. Jump by 2. If I say 0 state, I can skip all the in between the numbers like 0, 2, 4, 6. I can only print even numbers. I can only print odd numbers. Generally, counter can be classified as it is a basically pattern generator. We can also label that as a pattern generator. It generates variety of patterns. Each source 0 and 1 combination is called the state of the counter. Whatever the counter state it is. If you have a 1-bit counter, it will have only 0 and 1. If you have multi-bit counter, it will have multiple states. That is called as a state of the counter. Okay, again we are using state. State means its present situation of a counter. That's called as a state. Total number of states the counter is going to go through is called as a modulus. I have come across mod counters generally. How many states it has got, counter has got. That is called as a modulus. Shortly we can call that as a mod also, mod m counters. If mod m counter means it has got m number of states. Suppose if it is a 3-bit counter, it starts from 0, 0, 0, all the way it will go to 1, 1, 1. How many states we have here? Totally 8 states we have. So it can be called as mod 8 counter. Understood this? M stands for here number of states. How many states? And states must be unique. States can't be repeated. You cannot say when counter is repeating, say for example 0, 1, 0, 1 twice. You can't say it is again having one more extra state. Unique states I am saying here. If counter is a 4-bit counter, how many unique states we have? 16 unique states. All zeros, 4 zeros to all 4 ones. That's called the state of a counter. So if a 4-bit counter, I will have 16 states, therefore it can be called as a mod 16 counter. So that's a name which we give here. The order in which the states appear is referred to as counting sequence. Sometimes you can go in increasing order, sometimes you can come in decreasing order. You can design a counter in such a way. That's called the counting sequence. Counter can also be, you can depict using a graph. That's one of the most popular way which we can indicate the counter. Such a graph is called as a state diagram. In our syllabus, we are not going to deal with much more about the state diagram, but when you deal with more and million machines, finite state machines, what we call, there we discuss about what is called as the state diagrams. Okay, you have to. The idea can be presented even in the form of a state diagram also. You remember in the module 1 what we said? Any verbal statements we converted them into the truth tables, right? Okay, recall that what we said in the very module 1. All our verbal statements, we converted them into the truth tables, truth table to the Boolean equations, then Boolean equations, we simplified it using K-map, Karnaugh maps, and various other tools available. And finally, we written logic diagram followed by the implementation. That's the logic design flow. But here, even there is another way which you can do the logic design, that is called state diagram approach. Normally, when you use any electronic based CAD tools, they will provide various logic design entry. Understand? How can you enter your logic design problem into the tool? One way is if you know truth table, you can directly enter it. Because verbal statements the tool will not understand. You cannot tell the tool by giving just a verbal statement as your problem statement, right? You have to convert that verbal statement into the truth table and give the truth table as an input to the electronic tool. It will convert them into the hardware, and finally you can implement it. That's one way. What is the other way? If you have a Boolean equations, okay, equations also can be entered into the tool. That's also another way of entering logic design into the tool. What is the other way? Because there is one more hardware description method that we are going to cover in module 4 and 5. Even that way also you can enter the logic design problem onto the tool. Because when you want to implement them in integrated circuit, when you want to develop the IC of your own, okay, so such problems can be, you have to define it in the beginning itself. Various modes of entry are, one is truth table, number 2 is going to be the equations, Boolean equations, number 3 is a text based. Even if you have an idea, if you want to develop IC, what you can do is you can write a Verilog code or VHDL code, and tool will convert that Verilog or VHDL code into the hardware. It will automate it. That's the third way of designing a logic circuit. And what is another way is this is a remote state diagram approach. Most of the tools they will provide you state diagram approach. That means they will allow you to enter the state diagram of your problem. You have to define your problem in terms of state diagram. And tool will convert that state diagram into the HDL and then HDL to the hardware. That's how the flow goes on. Understood all of you? What are design entries? Design entry is the first step in the logic design. How do you enter the design? If I give you some problem, say for example, I may ask you to develop an adder. What are the various modes you enter adder design into the tool? Because you can't do by manually. You can't take adder IC and do it nowadays, because when I say build 1024-bit adder, you can't go to lab and do the adder. You have to automate that. How do you automate that? What are the design entries you have? As I told you, number 1 is, if you know the adder truth table, you can directly enter into that. But I don't suggest a truth table based adder because it consumes a lot of memory. Understand? You may say that how it consumes memory, because see, once you automate the truth table into the hardware, the automation tools will take a lot of memory in building the circuit. You are not building the circuit, right, for 1024-bit. You are telling the tool to build the hardware. In building that hardware circuit, the tool will take a lot of memory. But industry will not accept if your tool is taking a lot of memory. What industry wants is the code or the input or design entry what you do, which should occupy small hardware, minimum hardware in the chip. Such a way you should build the hardware. Okay. Anyway, I just want to tell you here at this point of view, you must learn state diagram. That's advanced way you can enter the logic design problems into the electronic tools. That's an important step. Okay. Any questions so far? We'll show one state diagram, how it looks before we proceed to the actual counter design. The state diagram looks something like this. Have you come across these things in any logic design textbooks, especially in finite state machines? You will see all design problems, adder, multiplier, subtractor, square root, any logic design problem you take, it can be represented like this. Understand it? It can be represented like this. Probably if you read the textbook authored by Charles Roth, very popular textbook. Okay. Unfortunately, that textbook is not there in your in the syllabus. It's very famous textbook, Fundamentals of Logic Design, authored by Charles Roth. Okay. If you refer that textbook, probably in the last part of this textbook, he will describe about how to do design entry using finite state machines. So the finite state machine, every problem can be defined something like this. Understand it? The finite state machines can be classified as Moore machines and Mealy machines. Today's problem, every problem is either Moore machine or Mealy machine. Understand it? Now you see we are going to the advanced logic design. So far what you learned is the basic logic design. If you jump to the state diagram based approach, you are going to the advanced logic design. From here onwards, you should conceptualize your problem, logic design problem, into the state diagram like this. Look at how we conceptualize the counter in the form of a state diagram. This is called as a state. Circle what we have shown here is called as a states. For a given problem, there can be n number of states. We don't know that. Some problems may take very few states also. We don't know that. Generally, the 2-bit adder, 3-bit adder will take just the 4 to 5 states. Understand here? When I say states, these are implemented using the flip-flops. Understand it? Okay, these are implemented using the flip-flop. Without that, you can't do anything, any sequential circuit design, right? Every circle represents a flip-flop here. So there is a counter here which starts from S1 state, and look at here, arrow mark shows that how the counter will progress from one state to the next state. And all these things, arrow mark indicates that it is upon occurrence of the clock pulse. Nothing will happen without applying the clock pulse. This arrow mark shows that you are applying some clock pulse, and present state is going to be 0, and state changes from S1 to S2 upon the occurrence of the clock pulse. Again, I don't say what kind of clock pulse you apply. You may apply positive level, you may apply negative level. In such a way, you can design the circuit. Understand? You can also design circuit such a way that whenever the rising edge comes, state may change from S1 to S2. You may design logic circuit in such a way that when the falling edge comes, it may change from state S1 to S2. There are various possibilities are there. But as I told you, rising edge and falling edge, again, it depends on which area you are located. If you are in the Asian belt, generally we use rising edge. If it is the US region and other part of the European region, some parts they use falling edge always. But I suggest you to learn both the techniques to do the logic design. You must do this counter design based on rising edge and falling edge, both. We learned, both the methods. And here in this diagram, this is called state diagram of a counter, which start incremental states from S1 to all the way Sm. So totally we have here m number of states in this counter. This is how the state diagram of a counter can be written. This is general state diagram what I have shown here, but you can write this state diagram for the specific, say, 2-bit counter, 3-bit counter. You can make it convert this state diagram into the corresponding the counter bit size what you have. This whatever I said, it's already written. The circle shows the states. It denotes the state of a counter, and arrows indicate here. The arrows what you are seeing here. This indicates it's a states, the migration from one state to the present state here. The counter cannot move in the reverse order. Counter has to go in the forward order only. That's how we have written the counter. And here few things are missing. When I say all problems can be converted into the state diagram like this, okay? What happens if the state doesn't make a progress? State can be one here also. Then maybe here self state also will come like this. Understand it? The state may jump from here to here also. It may be possible. Okay. That you come across when you do the real design. Don't expect this is a counter. Basically, we expect here increment from S1 to S2 and S2 to S3. But there are designs such a way that you can jump straight from S2 to S3 or S5 or S7. Something like you can do random jump. That's how the problem can be defined. Okay. So when you do the design, logic design based on the diagram, you'll understand all those kind of things. But this is the preliminary stage. So I would suggest to understand how do we represent the state, what arrow mark indicates. These are the basic things you need to understand in the counter. Try to understand counter very well, because we are moving slowly to the advanced logic design from the basic logic design. Let's take an example of binary ripple counters, and later we'll expand this how this binary ripple counter works. All of you have tested this ripple counter in the laboratory? Yes or no? You have done this experiment or not in the laboratory? No? Okay. Do you have this experiment in the lab? You don't have this. The same thing which comes. Same up counter. I have designed up counter. I have done experiment on that. Same thing here. This ripple counter, what I'm saying is, the word why I give binary is because it counts binary numbers, right? We don't do any decimal counters. We develop only binary counters. When I say binary, the output of a counter is 0 and 1 only, nothing else. Understand? Counter can count from 0 level to the higher level. That's called up counter. You can also do down counter also. From higher level to the lower level, you can make the counter to count. That's called down counter. You can also do bidirectional counter also. It is possible. Understand? So either way you can do the count. After reaching the final state, you can ask the counter to reset to the beginning value, and the counter can start counting. You can do variety of counter design. Anyway, I will tell you later on why this is called a ripple counter. You might have heard this ripple already in the adder also, right? Yes, sir. We have done ripple adder. Why do we call ripple adder that? What is the reason behind calling ripple adder? Cascade in many stages. Okay. You want to cascade many stages. What do we achieve by cascade in many stages? Is the advantage? Cascading many the subjects also. We cascade amplifiers also, right? Why do we cascade amplifiers? Higher gain, what higher gain, right? Single stage cannot provide sufficient gain. You want to cascade that and make the gate as a product of individual stages. It's not the cascading advantage. Okay, but see that if noise propagates at one of those stages, again it will be too late, it will get amplified. That's one of the problem in cascading arrangement. Anyway, that will not happen in the digital, because one of the advantage of digital is noise cannot enter the digital system. Noise can get smaller, like spikes what I mentioned. Understand it? That can be easily removed by using some noise can be eliminated by using some kind of logic. It's possible. That's why these digital circuits are noisy circuits. Rarely you will see the noise, but analog circuits are not like that. When I say sine wave here, a complete cycle, it may corrupt with the noise. It's very difficult to remove noise in analog systems. Whereas in digital systems, you can easily remove the noise. Suppose if the high level is occupied with some noise, can't you remove that? You can do that, right? Use some inverters, that's all, it's over. The output of inverter is noise free. See? Understand what I'm trying to say? Okay? So that's one of the advantage of digital circuit. That's why people is fascinated about digital design, because it's noise free. Okay? But you must properly interface the ICs, otherwise you end up with some the errors. Anyway, ripple counter is because the one counter, one flip flop we connect to the output of the other flip flop. And why we call ripple is because who is going to initiate the count here? That's a clock pulse now. For every flip flop, suppose if I'm using a 4-bit counter, for the clock of every flip flop comes from the output of the one flip flop. Understand here? The first flip flop output I will connect, I will feed that to the clock input as next flip flop. That's called the ripple count. I will show you the logic diagram. You'll understand better when I discuss that. But here try to understand that binary counter means it counts in binary numbers only. It doesn't count in any other number systems. Whose counting system corresponds to that of the binary numbers are called binary counters. Binary numbers, we have 2 to the power of n possibilities, okay, where n indicates number of flip-flops. Okay, if I say 2 to the power of 3 counter, how many flip-flops you need for that? It's a 3 flip-flops, right? If you want to build a 8-bit counter, okay, convert that 8 into the 2 to the power of something. 8 is nothing but can be expressed as 2 to the power of 3. That means you need 3 flip-flops to build 8-bit counter. If somebody asks you 1024-bit counter, how many flip-flops you need to build 1024-bit counter? Express 1024 as 2 to the power of something. 2 to the power of 10 is nothing but 1024. That means you need 10 flip-flops to build 1024-bit counter. When I say 1024, what's the minimum number, binary number? All 24 bits, all 1024 bits are 0. Understand here? And remaining, higher bits are going to be, higher level is going to be the 1. You can build 10-bit counter like that. It counts from all 10-bit zeros to all 10 ones. Okay? That's a 1024-bit count. Thus, you can also build small counters and binary up counter you can build, binary down counter you can build. The various possibilities are. Let us go through this 4-bit, because from our syllabus point of view, we don't go for higher the counter. Only we stick to the 4-bit counter. We try to explain synchronous counter and asynchronous counter. Okay. Later we'll try to understand difference between them. Now first let me go through the 4-bit binary ripple counter. Look at the logic diagram of that. Okay. This logic diagram is very simple. As I told you already, there is various signals you just understand. Try to understand here. All are D flip-flops. And look at the counting states. It starts from 4-bit counter here. First of all, when I say 4-bit counter, it starts from all 4 zeros. How many states we have here? 16 states. Understand here? 16 states. Number of flip-flops required is 2 to the power of 16 can be expressed as 2 to the power of 4. You need 4 flip-flops to build 16 state counter. Okay? 16 states are there. You can have the 4 flip-flops here. And look at all the T flip-flops used. We have used here. That's one of the most widely used flip-flop. You can also use, as I mentioned already, JK. And you can also use what is called as D flip-flop. You can use any of these flip-flops to build the counter. Okay, this is ripple counter. Why we call this as a ripple counter? You can see where the clock is coming for each and every flip-flop. For the first flip-flop, you can observe here, clock comes straight away from the input, from the user. And look at the subsequent flip-flops. You can see here, this is a complementary output of the D flip-flop, right? Just recall what is the truth table of a D flip-flop. Whenever there is a 0 input, it retains the present state itself. There is no change in the state. Whenever you apply T as 1, it will toggle. Understand here? The output will toggle when the T is going to be 1. That means you have to ensure that this is 1. This input is nothing but what we are calling is count enable. Always, as long as count enable is 1, these flip-flops will keep on toggling. And also observe here the D input is going every flip-flop here, right? But clock is not same. Clock is coming from output of this complementary output of the first T flip-flop will be the clock input of the next T flip-flop. And look at here again. This is complementary output of the second flip-flop is the clock input of the next flip-flop. Like that, we connected in the form of the ripple. That's why this is called ripple counter. If you connect clock to the every flip-flop simultaneously, then it becomes what? Synchronous counter. This is called asynchronous kind of counter because it's also called as a ripple counter because the clock has to ripple through all the flip-flops. That's why this is called as a ripple counter. Okay. So each positive transition from logic 0 to logic 1 causes the flip-flop to toggle the state. That means whenever you make some changes to this count pulse here, this is very important to change the state. First flip-flop, it will toggle whenever there is here the raising gate. Also, you can see that there is no bubble here. That means it's a raising gate triggered T flip-flop. Whenever the raising gate comes here, then this flip-flop is going to change its state. These are all not level triggered, they are all edge triggered flip-flops. Understand here? If I don't mention any arrow mark here, I'm seeing an arrow mark inside the flip-flop here that shows it is an edge triggered flip-flop. And there is no bubble here, means it is a positive edge triggered flip-flop. If you want to mention, write this as a negative edge triggered flip-flop, then you are supposed to indicate bubble here. So we have used here positive edge triggered T flip-flops, and output of complementary output of one flip-flop is connected to the clock input of the next flip-flop. This kind of the counter is called as a ripple counter, or also called as a synchronous counter. It's a 4-bit, of course, because it starts from a count value starts from all 4 zeros and it goes from all 4 ones. These are all the outputs here. Q0 is the first flip-flop output, Q1 is second flip-flop, Q2, Q3. These are all the 4 outputs, and you will see the states changing from like this. Q0, you can see here, this is written here in the form of the table here, and Q3, which is written here, and states start from initially, when you switch on this counter, when the clock pulse is not applied, it will be the initial state like 0, 0, 0, 0. All 4 will be 0. When you apply the clock pulse, what happens here now? As I told you this, when clock pulse is applied, when the T is 1, what the flip-flop will do? It will change its state. That means here 0 becomes what? It 1. We already know the property of a T flip-flop, right? What requires T flip-flop? Raising edge is required and T must be 1. T is nothing but here in this case, it's a count enable. If you make count enable as 1 and the clock pulse, if it is continuously, if you are applying the clock pulse, count pulse, then this flip-flop will change its state. That means every time when the raising edge comes here, this will change its state. You are observing here Q0 column, right? Just observe Q0 column here. Q0 0, 1, 0, 1, 0, 1. So every time it is going to change its state. Initially it was 0 before you turn on the counter. Before the raising edge comes, it was 0. The moment you apply the raising edge and T is 1, it changes its state to what? 1. And again, if you apply second time the clock pulse, it will change to 0. Again, apply clock pulse, it changes to 1. So that means every time the clock pulse is applied, it will go on incremental change. It will toggle from one state to the next state. Now, so make an observation here. We showed just now when Q0 toggles. At same time, observe when Q1 toggles. When the Q1 toggles. Just now I explained you when Q0 toggles. Understand here? When Q0 toggles. Q0 toggles because for Q0, this is the first flip-flop output. The clock what you are applying is straight away from the user itself. User keep on applying a lot of clock pulses here. And whenever raising edge comes here, it keep on changing its state. Initially it was 0 and it changes to next state as 1. And again apply clock pulse, it changes to 0. Again apply clock pulse, it changes to 1. That means flip-flop, T flip-flop is in the toggle mode, right? My question to you is now, we identified now when Q0 toggles. Similarly, when Q1 toggles, when Q2 toggles, when Q3 toggles. Look at here, one here, when there is 0, 1, look at here now. So flip-flop changes its state when this, because of the complementary output of this, right? Understand here? Complementary, we are not giving here normal output to the clock input as next flip-flop. We are giving what? Complementary output of the first flip-flop will be the clock input for the next flip-flop. That means always you should see here 1 to 0 transition here. Understand here? When there is a 1 to 0 transition in the Q0, at that time the Q1 makes a toggle. Q1 will be entering into the toggle. Are you seeing here? So 1 to 0 transition, what flip-flop has done here? The first flip-flop. I mean the second flip-flop here. Initially it was 0, and when the moment it changes to 1 to 0, why it is 1 to 0? Why it is 1 to 0 I have taken it? Why the flip-flop Q1 changes whenever there is a transition in Q0 from 1 to 0? So you are seeing normal output here, right? This is our normal outputs here. When I apply the clock pulse, what is happening here? This changes from 0 to 1. Understand here? At the same time, what is happening here? Complement of Q0. If this is going from 0 to 1, don't you think that this goes from 1 to 0? Because it's a complementary output, right? Understand here? But this is going from 0. Initially, I assumed as 0th state. And when I apply the clock pulse, this changes from 0 to 1. That's what we are seeing here, 0 to 1 transition. At the same time, what will happen to the Q0 bar? This is Q0 bar. It is making transition from 1 to 0. Understand it? So when there is a 1 to 0 here, you can see 1 to 0 here, this will change its state. Understand it? This will change its state, Q1 changes its state, and again you can see here, when Q2 will change its state, again there is a 1 to 0 transition. Look at it, 1 to 0 transition, this will change its state. This has changed its state. And look at here again, when Q3 changes its state, so far it was 0, and you can see here 0 to 1 transition was there here. Okay, so here you can see 1 to 0 transition has happened. When there is a 1 to 0 transition in the previous flip-flop, I mean the Q2 flip-flop, the next flip-flop will change its state. So far it was 0 here. When there is a transition from 1 to 0, Q3 changes from 0 to 1. Understood these things? But anyway, this will be clarified more through the waveforms. If you still have any questions, you can ask me in this counter. All of you understood how to construct, first of all, 4-bit ripple counter? Any questions in this? In this slide, what you need to understand here is the connections, how you make for this to design the 4-bit. You are not designing here. Of course, you are constructing the ripple counter. And you must also know the states, how many states this 4-bit counter has got. Totally, it has got 16 states. Q0 is nothing but LSB, and Q3 is nothing but the MSB here. Okay. And as I told you that whenever the clock pulse comes, this T flip-flop enters into the toggle mode. When there's a 1 in the T input, it will enter into the toggle mode. Look at this waveform. Try to understand this waveform. So far, whatever I explained, it will be clarified, understood with more detail with the help of this waveform. So first thing, Q0. On what basis you see Q0? How, when the Q0 will change its state? Just now, so far we explained that. Look at again circuit, because this entire circuit operation is explained through the waveform. You are going to see this waveform in any CAD tool if you design this counter. Look at the clock pulses, how clock pulses, count pulses comes here. Look at here. Okay, this is a train of pulses, right? It's clock pulse here. Now what you are supposed to see for the Q0 to change? Rising edge, right? If you have confusion, what I suggest you is always make rising edge like this, arrow mark like this. You will understand better at that point of time when the rising edge comes, then this Q0 is going to change its state. Look at here, there is a rising edge. Clock is going from 0 level to the high level. At that time, what will happen to the Q0? It changes from 0 to 1. Yes or no? That's a Q0. But every time when the clock rising edge comes, see what is happening here. This rising edge is coming, second rising edge is coming. Understand it? This is the first rising edge. First flip-flop toggle. Toggle means what? 0th state will be converted to the 1 state. So 0th state was here when the count was 0. When the flip-flop, when the count pulse was 0 to 1, Q0 changed from 0 to 1. And look at here now. Again, when for the falling edge, it doesn't do anything, right? We are not interested in falling edge. Only we are interested in rising edges. Observe always where rising edge. Here one rising edge is there, 0 to 1 transition, 0 to 1 transition, 0 to 1 transition, cut all these rising edges. Probably in your notes you can make some arrow mark to indicate the rising edges. You will understand better what is happening in the Q0 for every rising edge happening and occurring on the clock pulse here. How you understood this rising edge occurred in the clocks, so flip-flop entered from 0 to change its state from 0 to 1, change happened. And look at here again one more rising edge comes. When next rising edge comes, what was the previous state? Previous state was 1, now it changes from 1 to what? 0. And again look at here, next rising edge came here. Understand? Next rising edge comes, previous state was 0 and again it changes to 1. You are getting LSB of the count, right? If you observe the Q0 waveform. Every rising edge flip-flop is toggling, changing its state. Understood now? Now what I need to observe to analyze Q1, Q2, Q3 now. Q1 is the next significant bit, right? Q2 is next significant bit. Q3 is going to be the MSB. Understand it? To understand a Q1, you must always look at what? Q0. Don't look at the clock pulse. Why? Because there is a ripple counter. The clock for the second flip-flop is coming from what? Complement of Q0, right? Okay. So look at here now. Now when I say complement of Q0, Q0 is here. Don't look at rising edge of this. Why? Because you are taking complementary output. No, you are not taking normal output, right? You are taking complementary output. Therefore, so when you are taking, though I have shown here Q0 here, but for the second flip-flop, Q1 flip-flop, okay, the clock is nothing but the complementary output of the first flip-flop. Q0 bar you are taking. Otherwise, what I suggest you is write Q0 bar also, you will get to know that. When you write Q0 bar, rising edge of Q0 bar will be the toggling mode for the next flip-flop. Understand this thing? If you have any confusion, just write below this Q0 bar, you will understand better. Understand it? Here the Q0 bar is not shown, suddenly we have shown what? Q0, but Q0 bar is going to be the clock of the second flip-flop. So therefore, so just observe the, instead of writing Q0 bar and observing the rising edge of that, what I suggest you is, just look at the falling edge of Q0 itself. Okay, if you look at falling edge of the Q0, this is the falling edge of a Q0. Look at what is happening here. Till here it was 0, even though the Q0 was changing, but look at when Q1 changes its state, whenever there is a falling edge of this. Understood? Falling edge in the sense, in the number point of view, how can you say that? It's 1 to 0 transition, right? That's what I was explaining in the truth table, in the counting sequence. So whenever there is a change from 1 to 0, okay, look at here what happened in the Q1. It changes from 0 to 1. And look at where exactly now again occurring 1 to 0. This 1 here and 0 change happening here. And look at here flip-flop now Q1 changes from 1 to 0. That means the second flip-flop enters into the toggle after every, look at here, this is entered into toggle. If you look at clock pulse here, after every 4 clock pulse it will enter into the toggle. But look at only this and try to identify when the flip-flop enters into the toggle. Falling edge, it enters from 0 to 1. Falling edge is here 1 to 0. Falling edge 0 to 1. That's how the flip-flop changes its state. And again observe this. And look at this when this Q2 changes its state. Q2 changes its state, again falling edge of this, right? Okay. So there we have a falling edge because we are taking complementary of Q1 and connecting to the clock input of the next flip-flop. So you observe the falling edge of this. At that time, Q2 changes its state. Understand it? Similarly, look at Q2 and Q3. When the Q3 is going to change its state, the falling edge occurs here. At the falling edge of Q2, the Q3 changes its state from 0 to 1. Understand? That means this pattern, looks like, it's like a 16 states we're going to get. If you write binary numbers here, 0, 0, 0, 0, 1, 0, these are of course MSB. Okay, if I start from MSB, 0, 0, 0, 0, 0, 0, 0, 1, it's like a binary number. Okay, that's how the numbers keep counting. There's nothing but 8 you can look at here. This 1, 0, 0, 0. What is that value? It's 8 equivalent. Okay. Already off the way here. If you reach here, you're already completed 50% count. That's how you should interpret the count. This is actually the timing diagram because this x-axis is the time axis and the y-axis is the logic level. It's always 1 year logic level. Okay. Any questions about this before we move on to the next one? Okay. I hope you understood now what are things you need to write in when we ask you to explain about 4-bit ripple counter. Construction first of all. Okay, you must be clear in the construction. Many times students make mistakes in writing the construction logic diagram. Practice 2-3 times to you become familiar with the construction. Next thing is you must indicate states. If there are more number of states, don't go for state diagram. It becomes very complicated. Write the state diagram in the truth table itself is sufficient. Just like previously we showed, this table itself is sufficient. If you try to expand this using a state diagram, you have to construct how many states? 16 states. If you have time in the examination, you can do that depending on the marks. Okay, let's come to the analysis of this counter. Okay, let's look at these points, important points to be noted from the examination point of view. This is known as ripple counter since a change in state of the Qi minus 1. We are coming to general notation now. What is Qi minus 1? I minus 1 is used to toggle the QI flip-flop. As we expand, is it clear now? Now see, we are making that to in the form of a sentence like this. Are you understanding the first point? How many of you not understood the first point? I'll read once again. This is known as ripple counter first of all. Since a change in state of the QI minus 1 flip-flop, okay, is used to toggle the QI flip-flop. In our case, let me give example. I used Q0 flip-flop to toggle the Q1 flip-flop. QI minus 1 in our case refers to Q0. Understand? QI refers to Q1. Got it now? So QI minus 1 flip-flop I am using to toggle what? The next flip-flop. Q0 flip-flop I am using to toggle the Q1 flip-flop. Q1 flip-flop I am using to toggle the Q2 flip-flop. Okay? That's what the first point tells you. Is it clear? Many times when we go through these general terms, we don't understand, but try to interpret with what already we have studied, discussed. Okay? I hope you understood the first point. The effect of the count pulse must ripple through the counter. We already seen that. The first counter, it changes its state. The output of that is going to change the state of the second counter. And third counter, third flip-flop will change its state after the output of the second flip-flop. Like that, the counter will go through the ripple. The clock of the each and every flip-flop will go through like a ripple. That's why it's called ripple counter. Ripple counter is also called as asynchronous count. I already given you definition why it is called asynchronous. Conversely, synchronous means what? You are not connecting clock like what we showed here. For every flip-flop, directly you are feeding with a clock. That's called synchronous. If you ask a question, which one is widely used, of course, synchronous count. We always ask you to design synchronous counter. Rarely we ask you to design asynchronous counter because of one problem we encounter in the asynchronous counter is propagation delay. Okay, that's what it is illustrated next. You can see propagation delay. Okay, propagation delay. There is a propagation delay between the input and output of a flip-flop. Don't think that flip-flop is free from propagation delay. Propagation delay. How do you define propagation delay? Amount of time taken by the logic circuit to produce the output when the input is applied. Every circuit, even if you take simple AND gate, OR gate, basic gates in general, they will have a propagation delay. Of course, it is very small, negligible amount. It is in nanoseconds. But most of the time when you try to experiment this logic gates in laboratory, you don't come across this propagation delay because the moment you apply input, your output is ready. Reason is, can you imagine nanoseconds? You can't even expect the nanoseconds to occur, right? Nano, first of all, 10 to the power of 9, minus 9, very small nanoseconds. Understand? By the time you apply input, your output is ready. If you want to see this in delay, you have to model them using some tools. Then only you will see the real delay, nanosecond delay in the tools. If you can zoom it in the tool and you can observe it, even cathode ray oscilloscopes also not good enough to show the nanoseconds and picoseconds. A better option is going to be either we can go for digital oscilloscopes. I hope our laboratories are equipped with digital storage oscilloscopes. There you can even see in microseconds, nanoseconds. You can capture the waveform. You can store the waveform. You can take a printout. All those things is possible through digital storage oscilloscopes. Anyway, propagation delay, I hope you understood. General definition of propagation delay. Even here also in ripple counter, we come across what is called as a propagation delay. Ripple behavior affects the overall time delay between the occurrence of the count pulse and when the stabilized count appears at the output terminals. Worst case is, suppose if you have a counter like all starting from ones to all going to the 0, since the toggle signal must propagate through the entire length of the counter, you can take just simple example like if it is a 16-bit counter, it's a down counter means all the way it should go from ones to zeros. Totally we'll have 16 states. Generally we'll define propagation delay for the asynchronous counter or ripple counter like this. Its propagation delay is n times the TPD. What is that n and what is that TPD? N is nothing but stage, how many stages we have. In our case we have seen 4 stages. Okay, 4 stages. And look at this TPD. What is the TPD indicates? It's a propagation delay time associated with each flip-flop output. Let's assume that each flip-flop has got 10 nanosecond delay for 4-bit ripple counter. How much time it takes? 4 into 10. 40 nanoseconds it takes. That's how you can imagine. If one flip-flop is taking, if it takes 10 nanoseconds to produce the overall count, it takes around 40 nanoseconds, 10 into 4 stages, 40 nanoseconds. Like this, we can use the general formula N into TPD to calculate the propagation delay of asynchronous or ripple counter. Any questions about this? Okay. So important things were highlighted here in the ripple counter or asynchronous counter. The propagation delay is also one of the important parameters. That's a drawback of this counter because when you compare with synchronous counter, the asynchronous counter has got more delay. It depends on number of stages. Okay. So this, let us see in further when we go for synchronous counter, how this propagation delay can be reduced. Because there we apply clock to every flip-flop, right? That reduces the propagation delay of the flip-flop. There we measure in different ways the propagation delay. Any questions about this? Now we'll move on to the synchronous counter. Look at the definition of synchronous counter, just opposite of what we have discussed about asynchronous counter. Okay. So synchronous counter, all flip-flops change simultaneously after the appropriate propagation delay associated with the single flip-flop. Okay. All flip-flop changes in state because you are feeding the clock when all the flip-flops at a time. A single clock, master clock, and you're giving that to every flip-flop. But the same thing has not happened in the ripple counter, right? Output of one is just like a ripple. You see in a still pond, if you drop S4, what happens? The vibrations, oscillations propagate from one to the corner of the pond, right? Okay. Particles will disturb, right, and propagates, right? That's the meaning of ripple. Understand it? Same thing, even in this also, data propagates in the form of a ripple. Counter changes its states in the form of a ripple. Okay, that's why they are named as a ripple counter. But here it is totally opposite in synchronous counter. We're giving clock to each and every flip-flop. Count pulses are applied directly to the control inputs. Control input in our case is nothing but a clock pulse. All are clock flip-flops only. When I say clock flip-flops, you can use even here also T flip-flop, JK, and D flip-flops to design a counter. We have one counter design, probably that is going to be the last topic of this module. We'll take up on design mod 6 counter or mod 5 counter and show you one of the design steps in counter circuit. Okay, all flip-flops changes simultaneously after the appropriate propagation delay associated with the single flip-flop. Here we should see the propagation delay of the individual flip-flop rather than taking the propagation delay of all the stages. Understand the difference between the delay in synchronous and asynchronous? In synchronous, we should see only propagation delay of the one flip-flop, whereas in asynchronous, you must see propagation delay of what? All stages. If there is 10 stages, 10 into propagation delay of individual flip-flop. That is the overall delay in case of ripple counter. Whereas in case of this synchronous counter, what is the propagation delay? It's associated with only one flip-flop because you are giving the clock to what? One flip-flop. So here, they are much better than the asynchronous counter. Look at circuit this and you can interpret this. What is the idea? The use in the design of this synchronous counter. Anybody can understand this? Yes, look at this. Any questions here? What's the idea, logic behind designing? Also observe here, inputs coming to the AND gate. That's what I want you to pay attention here. Where the AND gate receives its input. Forget about flip-flops. Got some idea? My question is now, AND gates from where they are getting the inputs? First AND gate, you observe it. First of all, what is the requirement of T flip-flop? What is the requirement? I would like to write here for your, many times we will forget T flip-flop. This is the P input and this is the thing but Q plus 0, 1, Complement. This is called toggle. Don't forget this. No change state. If you apply 0 input, flip-flop will not change state. No change means if the present state, if you assume 0, next state remains as 0 only. If the present state, if you assume as 1, next state will remain as 1. Toggle is just opposite of it. If the present state, if I assume as 0, next state will be the 1. Present state, if I assume as 1, next state will be the 0. This is called toggle. That's why it's indicated as Q bar. That happens only when T is 1 and you must apply the clock pulse, rising edge clock pulse. The rising edge must be applied. Rising edge must be applied. Then only it changes its state. So the same thing is here. Clock must be rising edge. T input count enable. This is tied to 1. Look at now AND gate where this is the input now. For AND gate, first AND gate, the inputs are coming from Q0 is one input and this is going to be the count pulse is another input, right? This is 1. If this is 1 and Q0 if it is 1 and T input becomes 1. When T input becomes 1, what is the state you can see here? It toggles. It enters the toggle. Understand? Now whatever AND gates are doing now, it is helping us to change the flip-flop to toggle mode, right? When AND gate output becomes 1, there are 3 AND gates are there. When they become 1, flip-flop enters into toggle mode. Understand? And one drawback of the circuit is, look at here, I will go more detail in the next class. 2 inputs, 3 inputs, 4 inputs. If you build a 5th stage, understand here, you will have 5 inputs. If you build 100th stage, what will happen? Your AND gate is loaded with what? More number of inputs. That itself is a drawback of this circuit. Of course, you can work on this. It's not a major problem in synchronous circuit. One thing is from previous topic to this, we have reduced propagation delay in this. Now, propagation delay for this particular circuit is not N into TPD. It is just a one flip-flop delay, that's all, and one AND gate delay, that's all, nothing else. That's a propagation delay associated with synchronous counter. But only drawback of this particular synchronous counter is number of inputs coming to the AND gates increases. Understand here? And we are observing here Q0 and clock pulse based on this changes its state. Based on the clock and based on this and based on this changes its state. Okay, we'll continue this in the next class. Okay, I think the things which we have left out, I'll be covering this in the next class. Any questions?